Alright, welcome back. We're on homework 2 in our thermodynamics course. Homework 2 is on energy and different aspects of energy like internal energy, heat capacities, that kind of thing, latent heat. So number 3 says, in class, we mentioned how internal energy and enthalpy were pretty close for a liquid. So, if you have a liquid, that's not too bad of an assumption. Okay. It's not exact, but it's pretty darn close. Okay. And the same thing for the heat capacities, that the Cp of a liquid is about the same as Cv of a liquid. Now, approximately, does that mean they are equal? No, but they're approximately equal. Because, commonly you'll see this kind of relationship, what we call this, gamma, and just because, so the gamma of a liquid isn't always 1, okay? It's saying that, it's close to 1, but it's not 1. And you might be like, well, so what? Well, this gamma term comes into play in terms of a property, and it might not sound like a property, but the speed of sound is a property, a thermodynamic property. You might be like, that's kind of weird. Yeah, it is, but it's easy to measure, and it gives us a lot of other thermodynamic stuff. But that's kind of things that you'll see in Chapter 5 or in Thermo 2 or whatever. So, but I'm on a tangent. Let's move forward. Okay, so it says, estimate the Cv and Cp for liquid water at 25 degrees Celsius using the steam tables. Okay. So, we're going to assume that Cp and Cv are approximately constant. Okay? We need to assume that. Okay. And then we need our formula. So Cp is equal to dt, think of that, at constant p. And then Cv is equal to du dt at constant v. Okay. Again, I assume these things. Okay. So if I go to my steam table, okay, so that the Cp is going to be pretty easy. The du might be a little tricky, but hey, we're going to figure it out, aren't we? Okay. So we can kind of approximate this by being okay. So Cp is about delta H over delta T at the same pressure. Okay. So if and again, so we need to assume that our subcooled liquid, is about the same as saturated liquid. Okay. So we're going to assume that. That's a reasonable one. So now we don't want to do 25 minus something or something minus 25. We want it to be centered around 25 to approximate it at 25. So really we want the enthalpy at 30 minus the enthalpy at 20. Okay. 30 degrees Celsius minus 20 degrees Celsius. Okay. And that should give us approximately our heat capacity. So if we go there, so we have 20 minus 30. Let's see, our heat capacity. Okay. The vapor, 125. 0.77 minus 83.94 over 10. Okay, so, I don't know, 42, yeah, so about 4.2 kilojoules per kilogram. Okay, that seems reasonable. Kilogram K. Okay. That doesn't seem too crazy, so to speak. Okay, for the delta U, we basically do the same thing. Now it'd be like, oh, well, it's not a constant volume. Well, the other one wasn't at a constant pressure. If we look at the volumes, well, the difference between the volume is 0.001004 and 0.101002. The volume is pretty much constant. So, yeah, it's probably okay that we can assume, you know, that. And so that one gives about, well, 125.77. It's actually, they are the same. If you look at the steam tables, the U and the H are exactly the same, so their deltas are exactly the same. Okay. Now, on the second part, do the same thing for saturated steam at the same temperature. Okay. So now we're looking at saturated steam. Okay. So now now our assumptions get a little wonkier because, okay, now the constant pressure is probably true, but our constant volume, that one's a little trickier, okay, because we have 32 versus 57. Those are not exactly, the same, okay. So, we could do a couple of things, okay. We could approximate what the temperature would need to be, what the enthalpy would need to be at those temperatures so that the volume was between them, but we're not going to do that. We're just going to assume, that, volume is constant. That's a very poor assumption in this case, okay? But for the sake of simplicity, for the sake of what this exercise is meant to do, it's going to be okay. Because we just want to see how different things are, okay? So if we look at the steam of it, so this one we have, for the H, we have, 205.56, so delta H minus 2538. Divided by the delta T is still, 30 minus 10. Okay, so that's about, 20. About 20. 20 divided by 10. So that's about 2 kilojoules per kilogram K. Okay, it's actually pretty close, but remember that saturated steam, so that's actually not, too far away from this one is what I really mean. In terms of the CV, though, the U, okay, so that one's going from 2.4 to 3, so you can see how much different those are right now. So 2.4, no, what am I looking at? Oh, 2.416. It's smaller. 2.402, also over 30 minus 20. Okay. So that's, what is that, about 14? Yeah, 14 divided by 10, 1.4. Okay, and again, on the homework, I want you to do this yourself. I want you to do these calculations explicitly. I want you to show all the work. I'm shorthanding things for the sake of time, really for the sake of space more than anything. But you can see here, that's pretty different. Now again, we make the assumption that the volume is approximately constant, but I don't think it would be that much different. It might be a little bit higher and a little bit lower. That's significant. That's almost 30% different. So you can see that as I become more and more and more like a vapor, that PV term really starts to have an impact. Okay, now, is it because of the pressure? Well, no, the pressure is actually the same, remember. What's different here is that volume. That volume is so much more different. And not just different from the liquid, but different at different temperatures. This volume is so much more temperature dependent as a gas than as a liquid. Okay, and why is that? Because the liquid is in Compressible. Incompressible. What does incompressible mean? It means, well, you can't really change the volume. You can, but it's kind of difficult.